Standard binary classifications usually includes both labeled positive and negative samples. However, for PU learning, only positive samples and unlabeled samples exist. As you can see the illustration here, on the left-hand side is the standard binary classification. They are both labeled positive and negative samples, and so it is very easy to classify. On the right-hand side, we can see that only positive samples are labeled and the rest of them are unlabeled samples. Actually, PU learning comes from reality. In practice, the training data may only contain positive samples and unlabeled samples. For instance, while we can label subscribers who had watched at least one Hunger Games movie as being interested in this genre, we cannot be sure about the interests of a subscriber who never watched a Hunger Game movie before. Similar examples can be found in disease diagnosis. For example, in chronic disease diagnosis, while we might consider a diagnosed patient to be positive, the much larger population of undiagnosed individuals are practically mixed with both positive and negative examples, since people might be undergoing the disease's incubation period or might just have not seen the doctor. Roughly labeling the undiagnosed examples or as negative will hence lead to a biased classifier that inevitably underestimates the risk of a chronic disease. To address this problem, our method is to leverage semi-supervised learning to address the performance degrades of importance reweighting method. To this end, we propose a novel SSL-based framework to tackle PU learning. First, we use dynamic increasing sampling strategies to progressively select both negative and positive samples from the unlabeled data. And then, we adopt mix-match, which is a semi-supervised learning backbone, to take full advantage of the unchosen samples in the unlabeled set. On top of that, we will leverage co-learning strategies to train two independent networks to avoid confirmation